Hello everybody, welcome back to the channel, and I'd like to welcome you all to a rerun of our seminar on the fundamentals of aerodynamics as part of our Explorica Motorsport series. My name is Saiduth. I am the Motorsport content lead at SkillShark EduTech, and I also work as a race engineer in the esports league. So just to start off with, we did have our webinar held yesterday on the 17th. Unfortunately, we had a few technical glitches and some of the videos that I was showing were not running at the right frame rate. So we're re-recording this session. So for the benefit of those of you who attended yesterday, I hope you have a better understanding as I review the topics once more. And for all of you who were unfortunately not able to join us yesterday, I hope this gives a good insight of what we covered yesterday. We'll try to keep this webinar around the 1 hour mark, and I'll try to adjust time accordingly. So without further ado, let's start. So what we'll cover in this webinar will comprise of various topics related to aerodynamics. Of course, the pertinent question that we all want answered is why you need aerodynamics, and that will be something that will get answered as the webinar goes on. So we'll start off with some fundamentals. We'll go through aerodynamic fundamentals, also have a small overview of fluid dynamics and some of the fluid dynamics concepts that you need to understand in order to understand how air flows over a car. We'll also go through few of the aerodynamic devices that are used in vehicles. Obviously, there are a lot of them that are used in race cars today, but we'll cover some of the basic ones, namely the front wing, the rear wing, and the diffuser underbody section. And we'll also go through how aerodynamics is used in different racing series, and have a lot of pictures at the end of the presentation. We'll start off with the first question, which is why we need aerodynamics. And to understand why we need aerodynamics, we need to first understand what aerodynamics is. So aerodynamics is basically the study of airflow around an object. When you look at aerodynamics, you always look at fluid dynamics. Air, of course, is a fluid. So in order to understand how air flows around an object, you need to know some fundamental topics in fluid dynamics. So it can pertain to an object moving through still air, an object moving through air that has velocity, that is an object moving through wind, or a static object in wind. So all these situations are involved in aerodynamics. Now, of course, vehicles go through air at incredible speeds. So it's very important to understand how this air goes around the vehicle, because air, after all, is still matter, and it does have an impact on how the car behaves as it cuts through. So we'll start off with fluid dynamics. Let's imagine you have a plate in still air. So let's just consider static air at the moment. So we'll start moving this plate through air with the velocity v. And as a result, there is a relative velocity. So when you look at it from the frame of the plate, the air that is around the plate hits it with a relative velocity of v. And as a result, you have two forces that act on the plate, or rather it's an effective force that we can resolve into two separate forces. So firstly, you have drag, which is generally taken to be in line with velocity in the opposite direction of this velocity. And then you have downforce, which presses the plate downwards, and that is simply because the plate is angled in that way. If the plate were angled the other way, that force would be upwards. And the reason for that is basically it can be inferred from Newton's laws. So if you look at that plate and then you look at it frame-wise, you first have particles that start before the plate, and as they move towards the plate, you see that they bunch up together, and then one part of that group of particles gets separated, so it goes underneath the plate, as you can see here, and then the rest of the particles continue moving towards the plate, and then they sequentially collide with the plate. So as you see, the first particle, the bottommost particle, and that line of particles hits the plate first, and then it kind of creates an effect where it pushes the rest of the particles upwards as well, and then the subsequent layers above also start hitting the plate. So effectively, all these particles hit the plate, and this continually happens based on how separated that flow is. But what we consider here is laminar flow, so it's all uniform in terms of distribution, at least up till the plate. So because all these particles collide with the plate, you have an effective force that's being applied on the plate. So the particles effectively deflect in this way, and you have an effective force acting on the plate. Now that can be resolved into a downward force and a horizontal force towards the right, and that's what is resolved as downforce and drag. So now another way to look at it is by using Bernoulli's principle, and this is more commonly used when you're looking at aerodynamics because it gives you a better understanding of how to relate pressure and velocity. It's easier to, it might not be easier to visualize per se. Of course, Newton's laws, it's easier to visualize it as as air particles colliding with the plate. But Bernoulli's principle gives you a better understanding of how pressure is distributed, and it helps you understand other shapes apart from just a plate. So in the case of Bernoulli's principle, of course, you have a higher pressure that's formed on top of the plate, and that is because air becomes slower. The movement of air is slower. Now, this is where you need to understand that pressure can actually be split into two types of pressure. So you have static pressure and then you have dynamic pressure. So static pressure is kind of like the potential energy that the air stores, and dynamic pressure kind of relates to the kinetic energy that the air has. And that's what Bernoulli's principle also states. So the sum of the static head, dynamic head, and then the gravitational head in any 2 points of a closed environment in a flow will be equal. So what that means is if there's more kinetic energy in one side of the flow, there's going to be more potential energy on the other side of the flow. Henceforth, in this presentation, when I say that there's high pressure, what I'll be talking about is high static pressure. Now we've all learned in school, in physics, that air flows from higher pressure to lower pressure, and that is higher static pressure to lower static pressure. So a lower static pressure region has higher dynamic pressure. It has more kinetic energy because the air is flowing at a higher velocity. So low static pressure equals high velocity. So if you remember this concept, then you can understand everything that's taught henceforth in the presentation. So of course the air above the plate slows down, and that becomes a high static pressure zone. And below the plate, it's sort of a pocket. In this case, there isn't much flow directly underneath that plate, so it becomes a low pressure zone because there isn't really any air per se present over there. And that causes a pressure differential, and it presses the plate downwards in that direction that I've shown you, and then it again gets resolved. So now that we've understood how a plate flows through the fluid, let's try to understand how aerodynamic forces are distributed with respect to velocity. So aerodynamic forces are proportional to the square of velocity. So increasing the velocity has an exponential increase in aerodynamic force, which is why you have a parabolic graph over here. So in this case, let's assume you have a downforce distribution and a drag distribution. This is simplified to a very high extent, but it's just for the sake of explanation that I've given you two different graphs like this. And you have a race car for which this graph is applicable. Now, let's say that the race car produces some amount of power, and that's applied to the rear wheels as torque. So you have drag acting on the vehicle and downforce acting on the vehicle. Right now, I've shown them at random points. Now, as the vehicle increases speed, you can see in this graph, if you increase the velocity, the forces are going to start increasing at a pretty astonishing rate. Now, you reach a point where the drag force is equal to the force supplied, the reaction force that's acting on the tires and pushing the car ahead. So that is what we call terminal velocity. The car cannot go any faster than that. So terminal velocity is a concept that you might have studied in school. So you would have studied a situation where a ball falls through air. So if you consider the viscous forces and the buoyant force acting on that ball in air, and equate it to the weight of the object, you reach a velocity where both of them cancel each other out, and the object can no longer go any faster. Of course, it doesn't just stop because it has its momentum. What happens is the effective forces cancel each other out, so the velocity stays the same because it no longer accelerates. So that's kind of the situation here. You reach a point where the car can no longer accelerate and it gets stuck at a certain velocity. Now, the culprit here, of course, is drag. So you want to reduce that drag so that you can increase your terminal velocity. It's always going to be there. You're going to always have a terminal velocity, either because you're limited by the potential of the engine, or you're limited by the drag. But the one thing that you really have control over is reducing that drag. And that is what aerodynamic design, a large percentage of aerodynamic design is focused on that. Another part, of course, is focused on downforce. So let's try to understand why you need downforce in a car. The requirement, let's say you have a turn coming up over here and you have a little car here. So it's just a rough sketch of a Red Bull. So right now, let's say you have a constant radius corner. Now, generally cars won't take a constant radius turn. They have a gradual turn in and then it becomes sharp and then it's kind of a gradual turn out. So generally the cornering process is not a constant radius situation. But in this case, let's assume for simplicity, this car has a constant radius. So it's going on a circular path. Let's assume this radius is R, okay? So when you turn through a corner, think of the inertia concepts that you've learned in school. You're obviously going to be thrown outwards. So if you take a ball, attaches a string to it, and then you start twirling the ball around, obviously the ball is going to inertially be pushed outwards, and then the tension in the string is holding it, and ultimately it goes in a circular path. Equal analogy can be applied to planetary orbits. So in this case, you have an inertial force going outwards, which is mv squared by r. And then you have the reaction forces from the tires, which hold the car inwards. And ultimately, the velocity is, of course, always going to be tangential to this path. So in this case, the lateral force outwards will be mv squared by r, as I had said. So it's proportional to the square of velocity. The static friction is what the tires produce. So we're looking at static friction here because we're trying to we're looking at a situation where the tires no longer slip with respect to the ground. You don't want any relative velocity because then the car ultimately starts sliding. Generally, the static friction is equal to mu s, which is the coefficient of static friction, times the normal load. Now, obviously, this is applied till a point where you reach the limit of static friction. Once that lateral force overcomes that limit, you get kinetic friction. So in this case, the limit of static friction is mu s times n. For Fs is not always going to be equal to that. It's always going to be less than or equal to that because the static friction, the reaction force is always going to be equal to that inertial force to maintain equilibrium. But you reach a point where that lateral force gets too high. And when do you reach that point? When your velocity is way too high, you reach a point where the static friction, it overcomes that limit of static friction, mu s times n. So at that point, the car will start sliding. So you want to prevent this from happening. So let's say in that limit scenario, you have Fs equals F lat, okay, and here Fs is the limit of static friction. If you increase the normal force, the limit of static friction increases, meaning you can get more grip through a corner, you can go through a corner faster. And the only other variable on the lateral load, on the lateral force, is the velocity. So in essence, if you increase the normal load and press down the car with an extra normal load, you get more potential from the car. You can go through the corner with a higher velocity. So this is the entire concept. If you can somehow push that car down and make the car grip better, you can go faster. How can you do that? Well, we just saw. You can use a plate, of course, to press the car down, but a plate has a lot of drag. So there are other devices that can be used, other shapes that can be used to better generate downforce without having as much drag. So now let's get to that plate that we were talking about. We have something called the angle of attack. So that's basically the angle made by the object that you're looking at the moment with respect to the flow. So as you increase the angle of attack, you basically angle that object more aggressively with respect to the flow. So in this case, of course, if you increase the angle, it's going to rotate counterclockwise, the plate, assuming the plate is moving towards the left or the air with respect to the plate is moving towards the right. Now, you have a certain plot for every single object, and in this case, after a certain angle, the plate will lose all its downforce because it can no longer sustain that flow. Flow will break free, flow becomes uncontrollable, and that is why there's a sudden drop in downforce. Now, a plate is, of course, not the best shape. It's completely flat and provides a huge area for flow to just hit it. There's no real ability for airflow to roll over it or curve around its surface. So we employ the use of something called the Coanda effect, which is basically a phenomenon which dictates that air or any fluid tends to stick to curved surfaces. and that's just the way fluids behave. Now there are different forces. You have something called cohesive forces, which are intermolecular forces that hold objects of the same material or particles of the same material together. So cohesive forces exist within the fluid itself, between different air molecules or water molecules, depending on what fluid you're looking at. So then you have adhesive forces, which are forces that exist between particles of different materials. So that is like the force between the air molecule and the surface that it's sticking to. So there are situations where the air tends to stick to that. So sometimes the adhesive force becomes higher than the cohesive force, and that's why fluids in general like sticking to curved surfaces. Of course, smoother surfaces provide better transitions and better movement of airflow around those objects. So let's look at what happens when you have an airfoil. So an airfoil is basically an aerodynamic shape. There are different profiles that are used. The NACA profile series, the NACA profile series, is very commonly used for understanding these phenomena. So here you can see in this graph, there is a point where this graph actually intersects the y-axis, and this means that 0 degrees of attack, the downforce is not actually 0. If it's a flat plate, it's just going to cut through air, no real force is going to act. But in the case of an airfoil, it still has the ability to generate downforce even when it's at 0 degrees with respect to the flow. And we'll try to understand that with different scenarios. And as you can see in this visualization, you do have more downforce for a given amount of drag in an airfoil. So that is the lift to drag ratio, or in this case, the downforce to drag ratio. And generally in motorsport, you can either call it downforce or negative lift, because it's opposite to the direction of standard lift. Now these profiles are obviously used in aircrafts to push the aircraft up, but of course we don't want that in a race car because it defeats the purpose of sticking to the ground. Now let's look at different angles. So we have 0 degrees, air flows through the air flows through space, and then it reaches a point where it hits the airfoil. At this point, of course, the airflow splits. So the flow above tends to be slower than the flow below, and that's simply because there's a greater curvature there's more distance and curvature on the lower part of the airfoil, which causes the air to actually rotate. So it adds an additional rotational element to the air, making it flow quicker. Now there are a lot of misconceptions and explanations where people say that people say that particles will split at this point, and because this length is more, it has to travel quicker. There's no need for it to travel quicker. It's not granted that it's going to travel quicker, and it's not always going to meet at that point. Flow underneath just gets accelerated because of the Coanda effect. Now this is very complicated when you look at the actual equation, so we won't get into that. But for now, take it for granted that airflow underneath that airfoil accelerates and goes fast, or rather it goes faster than the air above. So because of that, faster air means that it has higher dynamic pressure, but it has lower static pressure. Slower air on top has higher static pressure. So you have a pressure differential that goes across this airfoil and presses the airfoil downwards. That's what happens at 0 degrees. As you can see, that is this intersection point on the graph. Now let's look at 10 degrees. 10 to 11 degrees is where airfoils generally start peaking in their performance. Simplified airfoils, of course, you do have airfoils that can reach much higher angles of attack. But in this case, let's look at 10 degrees. So air reaches this point, it splits, and it goes over, as we see. So this is a lot slower than in this case because it's being hindered by this airfoil. It's having to curve through a much smaller radius, which makes it lose its momentum faster. So there's a lot of high pressure being developed here, and then you have extremely low pressure down here because air is accelerating. It's going a lot more gradually with respect to the air around. So you have ambient airflow over here, and then you have the airflow that goes on the surface of these airfoils. And you see this point where flow starts separating away. Basically, the adhesive forces hold these fluids to the surface, and then you have the high energy flow here that rips the flow off that surface. And that's where Reynolds number comes into play, and it kind of tells you how aggressive or how turbulent that flow is. So there's only a certain angle up to which you can actually sustain this flow, after which you start separating, the flow starts separating. you reach an aggressive angle like 15 degrees, and what happens is air completely breaks off, and that causes two issues. Of course, you have not as much of a pressure differential because you don't have much air going through this area. It's more of static air present here, right at that separation point. And then you have extremely turbulent air that's coming up over here. And generally, turbulent air has a lot of velocity. But what happens is you also have turbulent air going over the edge of this airfoil, because at this point, air tends to curve over the edge. So both these two issues, basically, these two turbulent airflows collide, and it creates a sort of high pressure zone over there. So air becomes disordered, but it's not fast enough to create low enough pressure. So depending on the pressure differential, you're either going to have less downforce or, in really bad cases, lift, and you don't want that. So this is called the stall angle, where the airfoil stops performing because it stalls. And you see a lot of these cases where they talk about aircraft stalling while climbing, and that's because they reach an angle of attack where the airfoil performance stalls. So that's kind of where that term comes from. Now, there is a way to re-energize that flow. If there is some way to send more air into this zone and re-energize it and decrease that pressure, you'll get rid of that issue, just to drive that turbulent flow away. So that's called flow re-energization. And I mean, why don't we make a little slot there? That's a good way to re-energize the flow, right? Seems like the only logical way to send air over there. There you go. As soon as you create a slot and send air through that, you re-energize that zone, thereby decreasing the pressure. And so the air starts sticking together. Again, those cohesive forces become strong. You get more laminar flow as opposed to the turbulent flow that was present there. Of course, you still have small amounts of turbulence over here, but it's not as bad as what it was before. And you can see in this graph, for that same angle of attack, we didn't do anything to this yet. All we did was create a slot. So for the same angle of attack, you have more downforce, and the effective graph also changes, that potential graph. Smoothen out those edges. Instead of having this little rough cut, let's join the trailing edge over here and smoothen this edge, and there you go, you have two elements. So this is how a multi-element wing works, and this is how most wings are created anywhere. If you look at, whether you look at motorsport or aircraft design, almost everywhere you have multiple elements. Always work better with reference to the flow. So it effectively also increases the total airfoil size. But these are of course basics. Now, without getting too much more into the depths of fluid dynamics, let's actually get to the fun stuff, the race car stuff. So you have something called the front wing, which is the first type of device we'll look at. Now, front wings are placed close to the ground, and what that means is they use something called ground effect. Now, even though front wings look really small in comparison to the rear wings, they actually produce a lot of downforce, and that's because of this ground effect. First part of the race car that air hits as the race car goes through the air is the front wing, and as a result, it actually accelerates air quite smoothly underneath it. And because this airfoil is so close to the ground, it creates this sort of channel, a little tunnel that accelerates flow. Looking at the continuity equation, and then if you also look at Poisson's law, when you look at flow through tubes and pipes, you understand that velocity increases when that area decreases. So here the cross-sectional area of the flow decreases, thereby increasing velocity. And when you increase velocity, the static pressure drops, meaning, so in this case, you have very fast flow, and that creates a downforce, an excessive downforce effect over here. So that's how the front wings work. If you look closer, if you get too close to the ground, what happens is the slow air on the surface of this, which is the boundary layer, and the slow air on the surface of the ground, which is also boundary layer, those two boundary layers start getting closer to each other, and the effective area through which fast airflow is present decreases. So the downforce effect also decreases. So there is such a thing as going too close to the ground. Also, if you're really close to the ground and if your vehicle hits like a curb or some sort of bump or dip on the track, so the vehicle has the tendency to bottom out and hit the ground and damage the wing. So you don't want that to happen. So that's why you need to have a good balance between being too close to the ground and being too far away from the ground. Now, because of that, of course, air can also start rotating in that area, causing lift at a certain point. Now, you have another there's another task for the front wing, and that's to direct air away from the tires. Now, a tire is a rotating element, and on top of that, it's a circular profile from the side view, and it's a cylinder effectively. That's one of the worst shapes you can have moving through air because it creates a lot of vortices. There's something called the street vortex if you want to have a look at that later on. So it's basically an analysis of air going around a cylinder or a cylindrical or circular cross section. It's called a street vortex. So the vorticity coming off of this sort of a shape is really bad. So in a way, open wheels are an aerodynamicist's biggest nightmare, but in open wheel racing, that's what the definition is. So you can't get around that. The only way to get around that is by sending air around that. So one of the things that you can do is send air above the tire by adding an extra element. Obviously, rules don't always allow this, and you need to change the angle of the airfoil, not just in this plane, but from the front as well, to kind of direct air around the tires. So that's another job of the front wing. Now, another problem with these tires is the edge of the cylinder. You have that circular edge present, it's not sharp, but it is still an edge. So because of that, air tends to roll over the edges and create this sort of vortex. Vortices can be controlled, but turbulent air cannot. And vortices can tend to become turbulent air downstream of the flow. And to prevent that, the issue with having that is it can get in the way of other components that are behind in the car and cause a lot of drag. Also, sometimes if the vortices die out, it becomes stagnant air, which again causes high pressure, and it's an issue. Anyhow, you have to actually prevent these vortices from getting onto the car, and that's another task of the front wing. Of course, you need to generate downforce, set a precedent for the downstream airflow, because all the air that hits the front wing, the way that air moves is dictated by how the front wing manipulates the airflow. Of course, you need to cool the brakes, which is what usually the air that goes underneath the wing is kind of directed to brake ducts. You need to send air to the engine, the side pods, send air around the driver and the headrest. So the driver's helmet is also like this rough spherical shape, and then you have the headrest behind. These are all high drag elements. You don't want all the air to be hitting the driver's head and pushing it back. So you want to actually try to get this air to go around and not go anywhere near the driver or his headrest. The air intake, that air box is right above the head, so you kind of need to direct air to get it there. Aerodynamic design of a driver's helmet is also really important, but that's a complication we're not going to get into here. And then you need to control the Y250 vortex. That's what is used to direct this tire vortex out of the way. So you might be wondering what Y250 vortex is. Well, Y is the Y-axis, which is across the car. 250 is the distance. So you have 250 millimeters. So you're looking at a distance of 250 millimeters across the center line of the car. That's where this vortex gets generated. And it's according to the rules, of course, you need to end your airfoil element somewhere around that point. So you have an edge, you have an airfoil edge present there. I'm not entirely sure how the rules have been changed, but for a very long time, it was at 250 millimeters, which is why the Y250 name came to be. So anyhow, what happens is you have a little vortex that gets generated over there, and then you also have vortices at the edge of the wings. And you can use that to your advantage. So you can see here that vortices get formed at the edge of these tires, and they go along the vehicle, and they get in the way of all these other components that are present on the vehicle. It makes for really bad airflow at the end of the day. Also, another potential risk is these vortices can get underneath the car and disturb the flow in the underbody, causing lift. Very dangerous, especially if you're going through a corner at a very high speed. So in order to direct that out of the way, you can actually make use of this Y250 vortex and this end plate vortex. And by sending it in a certain direction and adding certain flaps below this, you can direct it outwards such that you push these tire vortices out of the way. So you send them out of the way of the rest of the car, and this actually helps a lot in improving the efficiency of the entire vehicle. So there are so many complications. It's not as simple as just putting some airfoils on a car and saying, yeah, I'm going to go super fast and win this Grand Prix. It's not that simple. There are a lot of complications that come up as you look at the rest of the car. So this is an interesting phenomenon. Now you have something called the rear wing as well, which is present at the back of the car. Now many people think the rear wing has a lot of downforce because it's really big. granted, it does have a lot of downforce, but it also has a lot of drag because of its size, and also because of the amount of turbulent air that's hitting it, you're going to have even more drag. So here you can see there's a high pressure zone on this side of the wing, and then you have low pressure behind it, which causes this drag. Or another way to look at it is air bounces off this massive wing and creates that drag. Either way, it's bad, and it causes a loss of speed in the straights. So F1 cars, and also if I'm not mistaken, LMP1 cars do have something called DRS, where they open one of the flaps of the wings, thereby reducing the drag. So if you open that wing flap, it makes for more smooth airflow through this little gap over here. Obviously the pressure decreases here because it's running a lot smoother at higher velocities, and the pressure differential is also less. It still will be there, of course, because these elements still have drag, but this element has very minimal drag. You reduce the effective drag on the rear wing, and teams use this to their advantage. Drivers use this to their advantage in races. Of course, they can only use it based on a specific rule set by the FIA, but when they're within a certain time limit, which is 1 second to the driver ahead, they can use this on specific parts of the circuit and gain an advantage. Of course, you don't want to open it. You're not allowed to, firstly, and you're not going to want to open it in the middle of a corner because that's going to spin your car outwards. You lose a lot of downforce by opening this rear wing as well. So it's not advisable, and it's not allowed to be done in corners. Then, of course, you have the need for end plates. So imagine you have an airfoil, a multi-element airfoil setup like the one I've shown here. So you have high pressure air on top of the wing, and then low pressure air beneath. And because there's an open edge over here, the high pressure air has a tendency to kind of roll over that edge and go underneath the wing, and this causes vortices. Vortices aren't always bad, but they're not good in this scenario because it basically disturbs the airflow underneath, and it creates drag and also causes downforce issues for this wing. So if you were to close off those ends, you can basically channel this airflow a lot better. That's why we use end plates, which channel the air and prevent the air from obviously rolling over the edge. Of course, the end plates also have edges, so ultimately the air will roll over it, but it's not going to have as big an effect because it has to travel a longer distance to actually affect the air underneath the wing. So you want to get rid of air in places where you don't want it, but it has to be done in a controlled fashion because you always want to control the air you're dealing with because it can potentially cause problems for your car. So that's kind of the function of an end plate. So the final device we'll look at is a diffuser. And let's take an example of this car over here. Let's say air flows through and hits the car. This is a rough shape of a stock car. It's not exactly its shape. I'm not saying that stock cars have bad aerodynamic profiles. In fact, they have really good aerodynamic profiles, but there are certain other issues with them which we'll get to. And as you can see a darker color like this orange over here, this dark brown orange, is high velocity. Green is moderately high velocity, and blue is low velocity. So air that hits this front part of the car just kind of hits it. There are some grills that send it to the engine, but there is a lot of drag over here. Low velocity means high pressure, so remember there will be high pressure in this zone. Now air underneath here, if you have an edge over here, air gets rapidly released. Okay, rapid expansion, it might be good because air is being sent back out and you have an acceleration of air, but it's also uncontrolled. And as a result, you have a lot of turbulence that gets formed here. Now the downside to turbulence is it's very low pressure. So turbulence has a lot of low pressure pockets that do. It's very difficult to tell where those low pressure pockets are and how big they are. Effectively, it's a low pressure zone. That's why it's in red. Now the issue with that is you have high pressure in the front, very low pressure at the back, and obviously you have very low pressure down below the car, and that sucks the car down. So you have the high pressure air on top that presses it down. You get downforce in that way. But this pressure differential also exists. And because of that pressure differential, you have a lot of drag. So that is what you call induced drag. And you get a lot of downforce, but you have induced drag. So there's got to be some way to release that air and make it more controlled. And luckily enough, there is a device called the diffuser, ingenious piece of technology. It's basically an expansion chamber. And as you can see now, the air is released a lot more gradually. You still have low pressure here, but the problem is it's not, but the advantage is it's not as low as before. And having this medium pressure zone here helps it, join with this flow on top a little easier. So this expansion chamber, firstly, it makes the air reach this point a lot smoother. But more importantly, it has a smaller, because of that, it has less induced drag also. But more importantly, it also has a lot of downforce added, because at this expansion point, there's a rapid expansion. See, it's still expansion, it's still rapid expansion, although it's controlled. And because of that rapid expansion, you have this sort of vacuum created here, and it accelerates air through that zone, and this becomes a low pressure zone. So you get some extra downforce at this point, which effectively presses the vehicle down. So a diffuser reduces the induced drag and also adds downforce. So it's a very powerful device, overpowered to an extent. I believe almost 40% of downforce is generated from the diffuser in certain racing series. We won't get into the details of design. There are a lot of other parameters, maybe in a future episode, but it's a little beyond the scope of what we're trying to cover today. Now let's look at NASCAR. Yep, NASCAR is an Americanized stock car racing series, often misconstrued as just cars going around in a big circle, but there's a lot more to it than that. It's in fact one of my favorite forms of motorsport. Very exciting sport, especially because there's a lot of aerodynamics involved in it. So what we look at is bump drafting. So what these cars do is they go in trains, or they make these trains of cars, and they all race bumper to bumper on these circuits called tri-ovals. So it's kind of a hybrid of a triangle and an oval, which is why it's called a tri-oval. So you kind of have that top part of a triangle, and then it opens up to be a sort of oval at the end of the day, and it reaches back to that point. So you have these super speedways like Daytona and Talladega. These are really high speed circuits where these cars run. There are a lot of other ones as well, but these are the main ones for that we can use for this example. So the first thing we'll look at is bump drafting. So bump drafting, as the name suggests, is bumper drafting. So let's assume air flows through the first car. So the first car is the number 15 over here. Then you have the number 24 that's trailing behind, trying to overtake him. So air hits the number 15, gets sent over the top, and then of course it follows that profile because of Coanda's effect. It hits that rear spoiler and shoots up once again. Obviously the rear spoiler adds a bit of downforce to this car, but that's not really relevant at this point. So what happens is the number 15 cuts through high pressure stagnant air. Remember, air is actually stagnant with respect to the car. So in this frame, when the car is cutting through that air, it is high pressure to start with. And then of course air goes below these cars, and these cars actually don't have proper diffusers or anything. So it releases air pretty badly behind. That causes turbulent air, and so the red obviously indicates high pressure. This green zone indicates low pressure. What happens because of that? High induced drag. So this car is doing all the work. The driver is trying to make use of whatever engine power he or she has to cut through that air. Now what happens to the 24? So you see these little pockets of air over here that basically amounts to less drag for the 24. So the driver is basically using this little pocket of air over here, which is a low pressure zone, to cut through and gain that slipstream advantage. So that driver, they would basically trail the car and gain a slipstream advantage and gain some speed. Now of course there is the benefit of the stream and it speeds up, but the 24 also releases turbulent air. But looking at this pressure differential, it's not as bad. So there are two ways to look at the slipstream. One is he's cutting through free air, and through Bernoulli's form of looking at it, the pressure differential is not as bad, and that's why it has less drag. So anyhow, the 24 accelerates, but that's not the end of the story. Now, as the 24 gets closer to the number 15, the air between them starts to get compressed. It starts to slow down, and the very presence of the 24 behind the 15 car increases the static pressure of the air over there. Now, because of that, the air pressure behind number 15 increases from what it was, and because of that, ultimately the induced drag also decreases. So now the 15 also gets to go faster. So that's the entire story of bump drafting. You have a car following another car, and then effectively both the cars' speeds increase. It starts with the 24, the 15 picks up as well, and then both the cars continue as a train. And as you add more cars to this train, your train goes faster. So a train of 3 cars is faster than a train of 2, which is obviously faster than a car that's just running on its own. So this is how drivers use bump drafting to their advantage. So in this case, of course, the 24 is gaining an advantage, but the driver is also helping the driver of the 15. So how does that driver actually overtake the number 15? Well, you can actually use bump drafting, or a form of bump drafting called side drafting, to actually increase the drag on the opponent in front. So let's see this scenario here. It's a different scenario. So the 24 is doing the 24 drivers doing their own race, and then you have the number 41 driver coming up over here. Now the 41, of course, the 24 has drag induced by extra air hitting the rear spoiler. That's just because the air, because the 24 is running on its own. It's not in any train at the moment. Now the number 41 has, of course, gained some momentum from the bump draft and now pulls out to the side. What happens because of this is air that's going around the 24, at this point, air gets squeezed in this gap and accelerates. It becomes high velocity air and it curls over the edge of this car and hits the spoiler. Okay, and because of that, you get extra drag that's induced onto that car. So as you can see, the air kind of rotates over here. You have extra drag induced on the 24 just because the 41 squeezes air onto that car. So in this case, the 41 used it to their advantage to overtake the 24. So this is what side drafting is. So this is another form of using aerodynamics to gain an advantage. So the first form helps your competition and yourself, and the second form is used to push the competition behind. So cars generally try to maintain the strain till almost the last lap, and on the final corner or the penultimate corner, they make this side drafting maneuver and overtake the car. So that's kind of how NASCAR works. Very exciting. I would really recommend you go and check out videos of NASCAR vehicles. It's a very exciting sport. Now let's get to aerodynamic balance, which is kind of the final physics element to the section. Hopefully I can cover topics which were not properly covered in the webinar due to time constraints. So now we have something called aerodynamic balance. Now, many of you would have heard of something called center of mass. You suspend an object at its center of mass, it won't rotate, basically, because all the forces get balanced. So forces always act about the center of mass. Very much like the center of mass is related to the inertial mass, you have something called the center of pressure, which is related to the aerodynamic loads. So in this case, let's assume you have the center of pressure located somewhere here on the vehicle. Now that could be caused by individual centers of pressure. So you have a center of pressure for the front wing, one for maybe the rear wing, one somewhere for the diffuser underbody, and then one for the effective shape of the car itself, because the car alone on its own can also contribute to some downforce based on how angled or wedge shaped it is. So all of these contribute to that effective center of pressure. And of course, that is dictated by how the air flows around the vehicle. So this is kind of a typical airflow distribution for a car. But now the presence of that aerodynamic pressure, the location of the center of pressure plays a big role in how the car behaves and how much downforce is distributed between the tires. So in the previous steering situation, we assumed all the tires have equal amounts of a downforce and the center of mass is at the center of the car. Here we'll assume the center of mass is at the center of the car. Those of you who understand the details of vehicle dynamics, you'll understand why I've taken it. But it's not really relevant at this point. We won't cover the vehicle dynamics of it. But right now, let's assume the center of pressure is on the center of mass. So you have equal distribution, which means that both the front and rear tires have the same amount of aerodynamic load. Now I've shown slip angle over here. Slip angle is basically an angle that's generated because the tire shears with respect to the ground. Again, I won't get to the details of this. We can cover this in maybe another episode on vehicle dynamics. But a higher slip angle means that your car generates more lateral force. Now what aerodynamics does is it increases the cornering stiffness, which means that you can get more lateral force for a given slip angle. So even though the tire might have the same slip angle limit, at that limit, you can have higher load. So if you have your aerodynamic center of pressure somewhere behind, towards the rear of the car, in that case, you have more aerodynamic load at the rear of the car. And what that implies is the rear tires get more aerodynamic benefit than the front. So that also means that the rear tires will fail later than the front. So in other terms, the front tires will lose grip before the rear tires, which means that the car will understeer because you lose front end grip and you kind of lose steering for a bit momentarily. Another way to look at this is if there's more load on the rear tires, like there's more aerodynamic load. Important to understand the difference. If there's inertial load, if there's inertial mass at the rear of the vehicle, it actually causes oversteer. Again, we won't get to the details of that because that has more influence in terms of lateral dynamics. But in this case, because there's more air, there's more downforce at the rear, the car gets pivoted at the rear. So when you have a pivot at the rear, the rear is planted and the front is not. On the flip side, of course, if you have downforce more at the front, the rear tires lose grip faster and the car oversteers and kind of spins out at the back. So now I'll attach a video file where you can see an explanation of how this is basically done and how different effects of the position of center pressure will affect the way the car handles. So let's check out that video and then we'll get back to some more discussions in this presentation. So now we'll see the performance of an LMP1 car around Watkins Glen with an understeer, oversteer and neutral setup. This is also a good idea for you to see how I would gauge my own lap time, my own driving style, and how you could replicate it for your own. So we're approaching the first corner, and here you can already see the amount of steering correction in oversteer while the understeering car just continues to plow through the corner. The understeering car also has a lot of drag by the looks of it because it's running way behind the others. The good thing about Watkins Glen is it's a track with multiple straights and a lot of high speed, medium speed flowing corners. It's a very good testing ground for the aerodynamics of your car. So coming to this fast chicane, neutral steer goes in pretty well. And you can see the understeering car seems to just struggle and it just overshoots the chicane while it goes to the exit of the chicane. Now we're entering the inner layout of the track. So neutral steer is ahead. Oversteer, again, you have a lot of steering corrections, and understeer is just at full lock, as you can see. This corner is quite straightforward. All three cars seem to be working in the same range with the same behavior. Getting to this section, you can again see understeer just plowing on ahead, almost going off the track over there. Now we're almost about to round up the lap. This corner is quite slow, so all the setups seem to work nearly the same. The upcoming corner is a high-speed left, and you can again see corrections in the oversteer setup, while the neutral steer and understeer seem to go through that fairly easily. And then we go through the final turn and wrap up a lap in Watkins Glen. Right, so hopefully that video was helpful and it helped you understand the differences between oversteer and understeer for different cars based on the wing angles. So something else to remember is you can get more downforce in the front if your front wing angle is higher than the rear. Not exactly numerically true. Basically, by increasing the front wing angle, you can get more downforce, but it depends on the design of the car to choose the right angle. Anyhow, let's look at one more aspect, which is understanding how suspension plays a role in aerodynamics. So a car has a basic ride height, which is how close the car is to the ground. And I told that depending on the position of this ride height, you can actually get different aerodynamic effects. If the ride height is too close to the ground, you might have negative aerodynamic effects. Sometimes if it's just close enough to the ground, you'll get really good aerodynamic effects. So let's first understand what a ride height envelope is. So let's say you have a distribution between front ride height and the rear. And at this point, the car is at its highest velocity. It's just about to start braking for a corner. Now, at this point, of course, it has its lowest front and rear ride height because the downforce presses the car down. So there is some compliance between springs and ride heights, which is why the springs get compressed. So the car has a natural state, a static state when the driver is in the car. And as the downforce presses the car down, it kind of moves with respect to the tires up till a point where it reaches its limit. So it hits those bump stops and it no longer goes lower. So this is the lowest point that the car can reach. Now the driver slams on the brake, the car pitches forward because it's moving, and as soon as you slam the brakes, it has a tendency to continue to move. So the center of mass of the car moves towards the front and it pushes the car downwards. Now at that point, the front ride height obviously dips and the rear raises slightly because of that. So the car will obviously roll about its roll center and effectively its roll center and the center of gravity. Again, we won't get into that here. And then the driver eases off the brakes as he or she gets into the apex of the corner. So as the driver starts turning in, the car of course starts rolling. So if the driver is turning towards this direction, the car would roll in the opposite direction. Anyhow, since the car is slowing down, both the rear and front ride height start to raise because there's not as much downforce at that point. Now, when you reach the apex of the corner, the car is at its slowest in this entire scenario. That's why it's called the apex. You got to nail the apex. The point where your car is the slowest, you have to make sure that point is perfect. So at that point, of course, you'll have higher ride heights in the front and the rear. And as the driver exits the corner, they slam on the throttle and the car pitches backwards. And that's why the rear will drop and the front slightly raises. But of course, initially the rear will drop and the front will raise, but since the downforce starts to act, the front also gets pressed down, which is why here you can see the front ride height is ever so slightly lower than in the previous case. But the rear ride height is of course dropped a lot. So this is what a cornering situation is. Now, why have I explained all of this? Because I want you to understand something called the ride height envelope. So that is the working zone, that is the ride height operation zone for the car. It doesn't go anywhere outside this. So all the positions and combinations possible for the car lie within this envelope. Now, why is this important? Well, your aerodynamic profiles depend on the ride height. So your downforce and drag will also depend on these ride height positions. So that's why you have something called the ride height envelope and aero map overlay. So this is an aerodynamic map here. So it shows you how much downforce or how much drag you will have in that envelope. So you want to design your aerodynamic devices to be within that ride height envelope. So when you're designing a car, you will already have a certain idea of how your ride height envelope is going to be, and then you'll have your aerodynamic devices designed in such a way that it fits somewhere within that envelope. Then again, when you go to a track and you start setting up your car, you can change and tweak your aerodynamic wing angles in particular to change the ride height around. You can also move the ride height envelope itself, and you can do this by increasing or decreasing the static ride height itself, and then decreasing and increasing the spring lengths can stretch and skew this profile as well. So these are the different ways you can actually manipulate this aerodynamic ride height envelope and the aerodynamic map to your advantage. It's something really interesting to see, which is why I showed this to you. So this is an image of a ride height envelope for a car. It's just a rough distribution. So you can already see from here that the red ride height envelope is a lot smaller than the green ride height envelope. At the same time, it has similar limits on this end, but not as much on that end. So you can already tell from this that the green ride height envelope is a little more skewed outwards and it has a lot more movement. So perhaps the suspension elements are a little softer, the springs might be softer. Something important to remember is spring stiffness determines how much the car moves, while damper stiffness determines how quickly the car stabilizes. So obviously a stiffer spring setup would have a smaller ride height envelope. Softer spring setup does have a wider ride height envelope. Anyhow, this is just a basic overview of the ride height envelope, and this of course is the aero map itself. So if I were to open this in the software and move these cursors to different points, I would get the aerodynamic balance at that point as to how much aerodynamic load is present on the front tires. Anyhow, that is a small overview of that. So now we've got through all the physics elements and how these cars actually work. To conclude, let's have a look at a few different cars, and this would kind of give you a good idea of some of the different innovations that have been used in these cars. So first thing we'll look at is the Lotus 78, obviously created in 1978, and it's known for its ground effect having sliding skirts. So these sliding skirts are basically wooden planks or cardboard pieces that were actually attached to the side of the vehicle. More in particular, it was actually at the edge of the underbody, and they were actually mounted on springs that were attached to the chassis. So effectively, it closed the entire underbody. So instead of air actually leaking out from underneath, it would seal that point. And what that does is it actually accelerates the flow to a much higher speed, and it's more controlled underneath the car. So these cars were able to reach absurdly high levels of speed through corners because of how much downforce they had. Great innovation, of course, but naturally it got banned because one thing, it is unsafe to have cars that can go that fast. And more importantly, they do keep changing these rules to make the engineering challenge a lot more fun, so that teams don't get complacent and get into one design phase. And I'm pretty sure all the teams really enjoy having these new regulations, because racing is, of course, it's fun, it's entertainment for some, it's a driving pleasure for some, but it's also that engineering challenge. And I think that's one of the crucial aspects in developing a race car. It's having fun and trying to build your car as close to the legal limits as possible for the rules that the competition is given. Anyhow, this is an iconic car from the aerodynamic history of F1. Then we come on to we come to the 2000s, so we jump quite a few years ahead, and this is the BGP 001, which is the bronze GP contender for the 2009 FIA F1 World Championship, and they use something called a double diffuser. So they had certain rules that limited how big a diffuser could be and where the diffuser chamber expansion point could begin, and this team actually used this to their advantage and found a loophole and created a small hole in the underbody somewhere before that zone where the expansion occurs, and sent extra air through a different channel to the top diffuser. And this gave a lot of downforce, and it was one of the features that helped Jenson Button win his first title in 2009. So coming to 2010, we have the RB6, which was the car that Sebastian Vettel used to win his first world title, to become the youngest ever F1 world champion. So that was the RB6, and what it had was the blown diffuser. The design engineer, the person who created this marvel, was Adrian Newey, who was regarded as one of the greatest design engineers in F1 for his time. He's done a lot in terms of aerodynamic development in the sport, and one of the things he created was this unique way of channeling exhaust gases to prevent any leaks from the rear tires into the diffuser. So the rear tires are constantly spinning, so there's a lot of air that's being generated, vortexes and turbulent air that's being sent out from beneath the rear tires. And also when the tire kind of goes on the ground, it squashes air underneath it and sends it out, so there's a lot of turbulence there. What happens is that ends up affecting the diffuser, because you want a good controlled environment behind the diffuser in order to make sure the expansion is also smooth. So what the blown diffuser does is it actually sends hot air to the sides of the diffuser between the tires and the diffuser, and creates this sort of channel, preventing any turbulent air from the rear tires to leak into that zone. That actually improves the diffuser's performance. Certain blown diffusers also send air directly through the diffuser, increasing its speed. And Red Bull worked with Renault to optimize some of their engine maps to make sure that air was constantly being blown through by the exhaust even when the driver was off throttle. So some extremely cool innovations regarding engine design, exhaust design, and aerodynamics all coming into one. So I felt the need to mention this iconic car. This diffuser race, this battle to make the best diffuser possible, went on till about 2013. Of course, from 2014 in the hybrid era, teams were forced to keep their exhaust in the center line of the car, right at the back, right under the rear wing. Of a turbo era car, because a lot of turbo cars were picking up then. But the reason I wanted to show this is because it has very basic aerodynamic elements. It's not as complex as the ones that are used today. So this is more in line with what we saw till now. So if we zoom in over here, you can see a basic airfoil profile. It's quite a simple multi-element wing, and you have a little step here in the front wing, kind of to replicate that stall situation to reduce drag. Quite basic designs. Of course, if you see in this view, you have these turning vanes. So instead of having that Y250 vortex that's being used to send air outwards, they had these little turning vanes and flaps and barge board. So this is like the basic form of a barge board that would send air outwards. So now let's look at GT3 cars. So these are used in slightly long races. Some of the series in which you see GT3 cars are the Blanc Pain series. You also have these cars present in the GT World Challenge series. So very popular cars, really good cars for driving. So these are based off production cars. So it's based off the M6, the actual BMW M6. Then they use the rules and they follow some of the rules and regulations set up by the competition to optimize the design and increase the performance. So you can see, a basic front splitter over here, which acts as the sort of front wing. You have an engine grille in the front where all the intake is taken in. Quite a big rear wing in the back, pretty complex diffuser you can see over here. Again, feel free to pause these slides and have a closer look at these these cars. Then you have something called GT4, which is kind of a slower variant of GT3s. So GT3s are around 500, 550 horsepower. You have GT4s, which run at around 400 horsepower roughly. So you can see major differences. This is obviously based off the GT of the M3, while this is based off the M6. But still, they have similar shapes. You see the splitters pretty similar to this one. Not as many small little knickknacks and aerodynamic devices on this car. Then another big contender in the World Endurance Championship, the Endurance Series, is the LMP1 car, which these are the highest tiered cars running in that series. So this is the Toyota hybrid from 2014. Again, a lot of aerodynamic devices. These are more comparable to F1 level aerodynamics. Now, of course, F1 aerodynamics is perhaps the pinnacle in terms of aerodynamic performance, but these cars are very close. Some people say that in certain circuits, LMP1 cars are actually aerodynamically better because they have less drag in certain scenarios. So they can be faster than F1 cars depending on the circuit. But these cars are more known for their engine performance. Their hybrid technology is marginally beats the F1 hybrid technology. Of course, F1 is limited to a V6 turbo, whereas LMP1 has certain other regulations and better powertrain capabilities. So something else to look into. Let us know. Again, we'll be attaching a feedback form with this webinar, and if you want to, we'll be giving you a choice of either having maybe an engine-based seminar or a vehicle dynamics-based seminar. So based on the votes that we get, we will be planning that in the future. So with that, I'd like to end this session. I hope this has been informative. There's been a lot of information that I've kind of thrown at you, so I hope you've enjoyed it. And if you're confused in any specific part, please do feel free to mention it in the comments below and we will get back to you. Also, feel free to keep looking at these videos multiple times. Keep watching this webinar. I'm pretty sure you'll learn something new every time you watch it. So as I told before, we have a feedback form attached in the description below. So we would be really grateful if you could fill that in. Let us know how you've enjoyed this session and what you'd like to see in the future. We do have a few options. Another piece of information, we do have an aero course that's being planned that will be released soon. So this one would obviously have the ability for you to get a certificate. So if you're interested in taking part in that, please do let us know in that feedback form. We do have some options asking you what you would like to learn from it, and we'll try to tailor the course according to what you prefer. One final piece of information is we do have an electric vehicle course coming up. As of the date that this video is coming up, it's still on, and we will attach that information which you'll see on the screen right now. So feel free to join and take part in that. We do have some opportunities coming up once you finish that course, so feel free to check that out. With that, I'd like to thank you for your time. Thank you for being a part of this. I hope you have enjoyed yourselves. Follow us on LinkedIn. We do have a lot of information coming up there constantly. This is Saiduth signing off. I'll see you guys next time.